Okay, welcome back. We've gone through our conceptual overview. Now let's move on to the practical overview for simple tables and figures. So in this, we're not going to get into the statistical software just yet, but rather just kind of a general overview of how we do this stuff by hand, or more about sort of the math and the steps involved before we go and actually walk through how we can do this using software, right? And so in this course, we will do these procedures by hand and also using software. Um, and that'll get more obvious as we go in the semester. Tables and figures might make less sense, but let's proceed. So for this first example, we'll go through two in this video. For this first one, imagine that I'm a consultant and I'm helping UAF with parking on campus. And so they're curious about people's commuting habits and they want to know, or after talking with them, I ask people how far they commute to UAF in miles, right? And let's say that I'm a lazy consultant or I'm just pressed for time. I don't know. But really, it's easier to explain when there's small numbers for the sake of our example. So in this case, let's only talk about 24 people, right? Because that's a simple approach to these things. So we can see this summarized in a table here, right? So here we can see the distance of the commute in miles, the people that responded within that category, and the percent of people surveyed that fell within that category, right? So in other words, we can see that 3 people said that they drive 18 to 19 miles, and that was 13% of the total, right? So we can see that our highest proportion, 37% of people drive 10 to 13 miles, and that was 9 out of the, what did I say, 24 people that I surveyed. Right, and so these are grouped frequencies building from our previous video. But this here is the finish line, right? I wanted to start with this to show where we can get to. And so what we're talking about in this example then is how do we get there from our raw data? And so in this case, there are kind of two broad steps. These steps vary depending on what you're trying to do. But in this case, we want to first identify the interval data, right? So these are called intervals, right? These sort of chunks or groups. And so we need to get our data on what the interval should be and how many people are within each interval. And then from there, we need to calculate what we call relative frequencies and percents to show the percent of the sample that responded in a specific interval relative to the entire sample, right? So that might sound intimidating, but let's go through it step by step. And so first, imagine we have our data here. So I said I surveyed that, well, English. I said I surveyed 24 people. And so we can see here miles driven or miles commuted actually is more accurate because I assume not everyone's driving themselves. So we can see here the raw data, right? And so we need to get from here to the table that you just saw. One of the first steps within that is to find the real range. And what this is, the real range is essentially the yeah. I was just about to say the real range is the real range. So let me just walk through it, and hopefully that'll make more sense. Um, when we're thinking about ranges, sometimes if we just subtract the largest from the smallest, that might feel intuitive or correct, but it's actually slightly inaccurate. So for example, if we sort this, um, and yeah, I'll put up a video or a link to how to do that in Excel. So if we sort the data, it's a little bit easier to understand, or you can start to see the overall trends, right? So we can see like, yeah, it's obvious that like 10 seems to be one of the most common, right? Just based off the groupings here. But if we just do 19 minus 2, we might say, okay, 19 minus 2 is 17, therefore that's the real range. But actually, that's not quite right. So our largest is 19, our smallest is 2. 19 minus 2 is 17, but the real range is 18, right? Because if you count out the individual numbers, 2, 3, 4, 5, all the way to 19, if you count those out on your fingers, you'll actually get to 18, right? And it's just this weird counterintuitive thing when we think about ranges that we need to subtract the smallest from the largest and then add 1 to get the full range that includes the largest and smallest options. Hopefully that made sense. But if it didn't, just follow this and you'll get the real range. Okay, so that's our first step. So now we have the range. Now let's work with the interval width, right, or finding the interval width. And the interval width is essentially the range of scores in each interval, right? So for example, if using dice rolls as an example again, Um, Typically, on a six-sided dice, each score is its own interval, right? The number of people who rolled one, number of people who rolled two, and so on. But say you kind of like group it into three intervals, then we would probably say, okay, the people who, or the number of times we rolled either a one or a two, and the number of times we rolled either a three or a four, and so on, right? So that's the interval width. To do this, we're going to follow these steps. First, divide the real range by the number of intervals that we want to use, which is arbitrary. We can kind of, we can kind of decide however we please or whatever suits the data best. And then we're going to round the quotient, right, the result of that, to the nearest whole number. So to put that in mathematical form, interval width equals real range divided by number of intervals. And again, we can pick this, right? And so generally the recommended number of intervals is between 5 and 20. That's what your book recommends, I think. But really it depends on what you want to do, right? Like if you're rolling, if you're reporting data from a six-sided dice, it makes sense that you have six intervals. If you're reporting from a three-sided dice, I don't know if that exists actually. I don't know. Let's say a four-sided dice, right? You probably want to report four, right? And so again, these are loose guidelines, but let's do five intervals in this example. And so our real range we said was 18, and 5 is going to be our desired number of intervals, right? So pull that from our previous calculation, divide by however many intervals we want. We get 3.6, right? So then we fulfilled that step. Now we need to round the quotient to 4, so 4 miles. That is the width of our interval. And so now let's construct the distribution, right? So so we're going to use the same number of intervals as what we just chose. That's pretty obvious because I was saying. And so to begin building this, let's start with the first interval. And so typically the upper boundary of that, or the lower boundary is just the lowest number, right? In this case, it was 2, because our range was from 2 to 19. And so we're going to start with 2, and we need to see how high that first interval is going to go. And so we'll take the smallest number plus the interval width, what we just calculated, and then subtract 1 from that. So in this case, again, the smallest value we got was 2, right? People drove at least 2 miles, everyone who responded, or commuted at least 2 miles, plus 4, the interval width that we got on the previous slide, minus 1, which is 6 minus 1, which is 5. Right? And so then, pardon me. So then we can say, okay, our first interval is 2 to 5, right? What we calculated there. Or in other words, the lower boundary is 2, the upper boundary is 5. And so we can then go through that step by step for each of the following intervals, and then this is what we yield. So there's a lot here, but I wanted to sort of overcompensate or over-explain. So our final intervals, you can see we have 1, 2, 3, 4, 5. That's what we wanted. And the values are 2 to 5. So in other words, if they commuted 2 miles, 3 miles, 4 miles, or 5 miles, the next interval 6 to 9, 6, 7, 8, or 9 miles, so on and so forth. Interval width, right? And so that is the sort of the range or the width of the interval in terms of the number of values that fall within it. We can see here that it's not perfect, and this usually ends up being the case that we kind of have a final interval that might be a little bit odd. Assuming it, I guess it really just depends on, how if we have odd or even numbers, and if we have an odd or even interval width, so on and so forth. But so here we can see our last interval, the leftovers, sort of were 18 or 19, so that's just 2 values. Lower and upper boundaries, there you have it, all in one place. And so let's flip it, right? So this was what we previously had. Let's flip it in this example, because I think your book does that quite a bit. And really, the choice to do this, to flip it, or show bottom at the top, or the furthest at the top, it's really up to you. But for the sake of our example, we'll just do it this way, because what I'll be explaining later makes more sense if we're thinking of it in this context. Okay, so we've got that. And to just explain this again one more time, or excuse me, so here we have our boundaries, right? So now we need to add the frequencies to that distribution within the boundaries or within the intervals. And so we can see here, 2 to 5, there were 5 people who commuted between 2 and 5 miles, right? And so we can even count that if we wanted to. Here's our sorted data. 1, 2, 3, 4, 5. Okay, 5 people fall in that interval. People that commute 6 to 9 miles, also 5. Right, so we can see 1, 2, 3, 4, 5. Yeah, my brackets are a little off there. But we can continue doing that, and this is the frequency distribution, right? So 9 people commuted 10 to 13 miles, so on and so forth, right? So that was the first step. Now we need to do a few other things or cover a few more topics. Cumulative frequencies. Cumulative essentially means like um, the lump sum, right, or the grand total as we're continuing to add things to it. And so this is just another example of a distribution. Um, yeah, and I'll show a table of it on the next slide. But we can add things from the bottom up or the top down, right? So in other words, we can add from the bottom up, right? So we could say 5 people drove at most 5 miles. We could say, if we add that, we could say, okay, 10 people drove at most 9 miles, right? Because there were 5 in this category, 5 in that category, so on and so forth. Or we can add from the top down and say 3 people drove at least 18 miles, 5 people, some of these drove at least 14, so on and so forth. Right, so different ways of approaching the same problem. And again, it's kind of arbitrary. It's up to you. If we add from the bottom up, the interpretations in this example, because again, they could change depending on your context, but in this example, adding from the bottom up, phrases like less than, at or below, so on and so forth. Adding from the top down, typically we're using phrases like greater than, at or above, at least, when we're explaining things. Right, and again, these apply in this example because we have our highest values at the top of the table and our lowest values at the bottom of the table. If we flip that, then this kind of becomes backwards. So just know that if you ever get confused, just think through what the data is showing and how you interpret it. In this example, let's start with adding from the bottom up. Whoops, my arrows are wacky. So I just went over this briefly, but we can say 5 people drove 5 miles or less. 10 people drove 9 miles or less, right? Because we're just adding 5 and 5. And the upper boundary in our interpretation is the upper boundary of that interval. 19 people drove 13 miles or less, right? So we're adding 9 to 10, and so on and so forth. And then our top cumulative frequency here is the grand sum of our sample, right? Because we surveyed 24 people, and guess what? 24 people drove 19 miles or less, right? They fell within the real range of our data. Or another way to say this is drove at most. Yeah, we can say 19 miles or less, drove at most 19 miles, right? Different ways to interpret the same thing. Adding from the top down then is essentially just the opposite. So if we're doing this, we'd say 3 people drove 18 or more miles, right? Now the lower boundary for our interpretation is the lower boundary of the interval. 5 people drove 14 or more miles, right? Because 3 were in this interval, 2 were in this interval, so it's a grand total of 5 falling within at least this interval or higher. 14 people drove 10 or more miles, so on and so forth. Right, and once again, we end at our grand total, 24, and just a different way of saying the same thing about our distribution. Right, 24 people drove 2 or more miles, just like 24 people drove 19 or less miles, right? Because everyone drove between 2 and 19 miles, or commuted between 2 and 19 miles. Other language, 24 people drove at least 2 miles, right? Again, different ways of explaining the same thing. So those are cumulative frequencies. Relative frequencies, it's more about the proportion of scores in each interval relative to the overall sample or overall distribution. And so to put this to math, relative frequency equals the frequency in interval divided by total frequency count. So for example, if we're doing a relative frequency for the furthest commuters, the 18 to 19 milers, we see our f of x is 3, and f of x, it's essentially a term for a function, in this case frequency. So we can see 3 people were in that interval, right? So that's the frequency in the interval. Total frequency count was, again, 24, right? In this case, total sample. And if we divide those two, 3 divided by 24, we get a value of 0.13. We can repeat this for the next interval, 14 to 17. We had 2 participants who fell in that interval. 2 divided by 24 is 0.08. Next one, 9 divided by 24 is 0.37, so on and so forth. Right, and so again, in this case, we're just calculating the individual interval frequencies relative to the total frequency. And these might be a little less intuitive to interpret. And really, I think the main importance here is to convert this into a percentage. And in this case, percent is just this frequency times 100%. So for example, 0.13 times 100 is 13%. Right, and so essentially we're just moving the decimal point over 2 spaces. So yeah, 8%, 37%, 21%, 21%. And our totals here should be approximately 100%. The way rounding works, you might end up with an odd value here, like 99% or 101%. That's okay, but in general, try our best to add these up to equal 100% to be as accurate as possible. And so once again, yeah, that was essentially all the steps to get to the table that I showed you at the beginning of that. Right? And so it might feel involved or intense, but really, yeah, this is just, it's a little bit tedious to explain it step by step, but this stuff can become second nature with practice. So that's the first example. Now let's move on to a second example. And in the first one, essentially what we were doing was walking through ways to take our raw data and then convert it into a frequency table to communicate that data more easily to other individuals, right, to whoever might be reading it. In this case, we're kind of talking about after we've already done something like that, how do we draw more information from the frequency distribution or from that table, right? And so in this case, or in other words, how do we use that data to inform some kind of decision? So for example, let's say that UAF, after they've done this parking study or whatever you want to call it, they want to incentivize public transit. Or maybe they just, I don't know, don't want people commuting as much. They're worried about car emissions, right? Something like that. And so to do this, to try to incentivize people to take public transit, they decide to raise parking prices for people, specifically for people who commute 15 miles or less to campus, right? They're saying you live close enough that you should be finding other options. I don't know. This is hypothetical. I don't think this would actually happen. But for the sake of example, let's say they did this. And so we're curious, okay, what percentage of our sample commutes 15 miles or less? Or in other words, if we had a sample that really did represent the whole university, this one probably doesn't because it was only 24, and I made this whole thing up. But if this was a representative sample, then we might say, okay, what percentage of our sample, which represents UAF, so what percent of UAF roughly commutes 15 miles or less, right? One example of how we might use this data to inform things. So again, here's the table we saw previously, but now we can't say that directly, right? We can't say, or we can't see here what percent commute 15 miles or less, and especially because 15 falls right in the middle of this interval, right? And so we can already see, okay, we're going to be doing not necessarily guesswork, but this is going to involve some estimation. And so we need to calculate some things in order to be able to more directly estimate that, because we could add these three up and say, okay, 21 plus 21 is 42, plus 37 is, 79? So we could say it's going to be more than 79%, but less than, 87%, right? So between 79 and 87%, somewhere in there. That's ballpark, though. Let's say our boss is a stickler and wants an exact number. So what we want to calculate then is the percentage of the sample that commutes 15 miles or less, right? We want that precise. And so in other words, we need new columns, right? Everyone's favorite thing. Let's add some columns to this. On that note, too, graphing or drawing a visual can be helpful. So this is an example of a bar graph that I just threw together on pad and paper. I'll probably do this a lot this semester just because I get tired of clicking with the mouse all the time. And so this here, yes, you can see like you can kind of do this to get a sense of proportion a little more easily. So we can see, okay, there's definitely a lot less people driving more than 15 miles. So it's going to be a high percentage that drive 15 miles or less. This is an example of a pie chart or circle chart for different terms. But so we can see here, let's see, 2 to 5 miles, 6 to 9, 10 to 13, 14 to 17, 18 to 19. So the percent that drives 15 miles or less, yeah, like this is going to be the slice of the pie, roughly, that drive 15 or more. And so it's going to be a big portion of the pie, right, that go 15 miles or less. So just some examples of how figures can be helpful. So let's do a few things here to get to relative percent. First, let's start with cumulative, or I'm sorry, we already had relative percent. What we need to get to is cumulative percent. So this, just like cumulative frequencies, we're distributing the sum of relative percentages across a series of intervals. In this case, typically bottom up, but they could vary. In this case, bottom up makes the most sense because, again, our high values are at the top of the table. So we did all this before, relative frequencies. Cumulative percent, then, we're just going to add up the relative percents, right? So this first one, if we're going bottom up, 21% of people drove 2 to 5 miles. Now we're going to add these two, so 42% drove 9 miles or less, 79% drove 13 miles or less, right? That was the mental math I did earlier. 87% drove 17 or less, 100% drove 19 or less, right? And so we know that it's going to be somewhere in this window. Oh, sorry. We know that it's going to be somewhere in this window, right? Because the upper end, 13 miles, was 79% of the sample. 17 miles was 87% of the sample. So it's going to be somewhere between these two, between 87 and 79%. So that's the number we need to get precisely. Some terms here, percentile rank and percentile point, because that's essentially the technical term for what we're looking for here. So these can help us to identify sort of an individual rank within this distribution. Yeah, these definitions are wordy. Basically, what we're doing here is we're taking our frequency distribution and sort of converting it to a cumulative percent distribution. And percentile point, percentile rank are kind of opposite ends of the same coin. So percentile point is the value of a score on a scale below which a specified percentage of scores in a distribution fall. Right, and percentile rank is percentage of scores with values that fall below a specified score in a distribution. So in this case, basically the difference between these two is what you know and what you're trying to find out. So here, for example, we know that we're looking for people who drove 15 miles or less. So that's our specified score is 15. And we're trying to find the percentage that fall below that, right? So 15 or less. So that, in this case, we're looking for the percentile rank of 15, essentially. If we knew the opposite, right? So we had a percentage and we wanted to see, okay, what was the score on that scale below which that percentage falls? That's percentile point, right? So say, for example, I was like, yeah, if we wanted to lower prices for, or if we wanted to raise prices for only 25% of people, right? How many miles is that, right? At which point we'll reach 25% of the sample, right? So hopefully that made sense. Point here is that they're opposite ends of the same coin. I don't think it's super important to know the distinction here. But so if we're going for percentile rank in this example, so step one is to identify the interval. Like I said, we know it's going to be somewhere in here because we know we're looking for 15. In this case, or next case here, is to identify the real range for that interval. And so this is the upper bound for reasons previously explained, right? 87% drove 17 or less, or commuted 17 or less. This is the lower bound, right? Because we know 13 or 79% drove 13 or less. So we know this is going to be the bounds for this specific example. And so our value will be between 79 and 87%. So we can kind of explode that a little bit. So we're taking this interval, we're kind of blowing it up to where, okay, the upper bound is 17, 87%, 14 is 79%, 15 is what, right? That's the percentile rank we're looking for. And because of rounding, it's important to note that our upper limits and lower limits are sort of 0.5 on either side of this. So for example, again, something I drew out. If we're looking at this on a scale from 0 to 19 miles of commute, right? Our range here, this interval, is 17 to 14, right? But really, if we zoom in a little bit, our real range kind of goes a little bit beyond that, right? 17.5 to 13.5, right? That's what this means and what your book's talking about when it talks about real range being 0.5 higher or lower than your limits. Just think of this visualization here. And so in this case, our real range is 13.5 to 17.5. Or again, just another way of showing that real range is kind of counterintuitive. In that here, if we just did 17 minus 4, that would be 3. We might think that's a range. But when we're thinking about real ranges, actually it's one more than that, right? It's going to be 4 because it's from 13.5 to 17.5, which is 4 instead of 3. Yeah, so the range width is 4. And that was the value that we calculated in the previous example. Okay, so step 3, find the position within the interval. Again, if you're looking for a percentile point, the number's over here if we knew the percentage. Your reading covers how to look for that. And it's kind of just the inverse of what we're doing here. But if we're looking for a percentage or percentile rank, let's use this formula below. Lots here. So let's walk through it. So we have upper bound minus percentile rank divided by upper bound minus lower bound. So we can see here, x is what we're looking for. X is percentile rank. And so we can plug that in first, right? We know that's going to be x. And this is essentially turning into an algebra problem. So if algebra wasn't your fave, I apologize, but we can get through it together. And then I color coded these. If anyone has issues with the colors, let me know. We can talk through it in other ways. But so we see here the upper bound was 87%. The lower bound was 79%. And we're multiplying that by range width, which again we said was 4. That's the width of the interval. And that's going to equal the upper limit, 17, minus the observed value, or 15. Right, so in this case, when we're talking about bounds, we're talking about the percentages, and we're talking about the limits and observed value, we're talking about the actual scores. And so if we do this math, 17 minus 15 is 2, 87 minus 79 is 8. So now we've reduced that a little bit. If you recall from algebra, in this case, our next step would probably be easiest if we just divide both sides by 4. And so we do that, and then we can get rid of the parentheses in this 4. So now we have a fraction problem, 87 minus x over 8 equals 2 divided by 4. Again, going back to algebra, when you have something like this, you have two fractions equivalent to each other. You can reduce them by multiplying the opposite side, or the opposite numerator by the opposite denominator. I really hope I got those right because I always mix those up in my head. Basically multiply the top by the other side's bottom. There you go. So 4 times 87 minus x equals 2 times 8. And we do that. That's going to be 16. We can go through this math and we'll find an x of 83. And so in other words then, 83% is the number. In other words, 83% of our sample commutes 15 miles or less. And to put that in a pie chart, this is what we see, right? So we were pretty close in our first interpretation of the pie chart. Yeah, 83%, 15 miles or less. Only 17% drove or commuted more than 15 miles. So in other words, in this hypothetical example, 83% of us would see raised parking prices because we commute 15 miles or less, which is very sad news because we don't want to pay more money. 17% of us would not, which is, I don't know, maybe good news, maybe just kind of whatever. But yeah, just another example of how we can use these distributions of frequencies to then interpret things in terms of frequencies or percentages. And so these are some basic statistics, but nonetheless very important to understand early on because these sort of concepts when it comes to proportions, frequencies, interpreting things from tables and figures, those are things that we'll build on throughout the course. So we'll go ahead and stop there, and we'll see you in the next one.